Okay, now let's continue along the lines of our discussion in the one-dimensional case. Now, what we did in the linear motion case, or not one-dimensional. Now, in the linear motion case, we first discussed the one-dimensional motion, and then we said we have vectors. The velocity is actually a vector. The acceleration is actually a vector. Now, the same we can say about the angular velocity. Angular velocity and angular acceleration, they are also vectors. But if you want to specify the angular velocity vector, just as any vector, this should have a magnitude and a direction. So magnitude we had already defined. It's the rate of change of a given angle per unit time. But when we are talking about the angular rotations, we said that, okay, we have to specify not just how fast it turns around, but around which axis it rotates. So we have to specify the axis. So if I'm spinning this wheel in this sense, it is rotating around this axis. So there's an axis around which my wheel rotates. But that axis already specifies a direction. So when I'm talking about the angular velocity, I have to specify these two things. I have to specify the axis, which is nothing but a direction, and the magnitude. That is what makes the angular velocity a vector. Now, of course, if you have an axis, it's just like the one-dimensional motion. It has two directions. We have to choose one direction for the angular velocity. And the direction for the angular velocity we usually choose by what we call the right-hand rule. Take your right hand. Okay, so if you are lucky, if you are not left-handed like me, if you are left-handed, you will quite often take your left hand, take your right hand, wrap your fingers around the rotation direction of the wheel. This is your thumb. This is the direction of the angular velocity vector. So in this case, when the wheel is rotating in this sense, the angular velocity vector is pointing upward. If it is rotating in the other sense, in that case, just take your right hand, wrap it around the axis such that your fingers, these four fingers, are pointing in the direction of rotation, then your thumb is pointing in the direction of the angular velocity vector. So the direction is determined by the right hand. Now, why the right hand but not the left hand? It's just convention. I mean, the majority of the human beings are right-handed, so that's why they chose the right hand probably. If the majority of the human beings were left-handed, then we would probably have the left-hand rule by this time. So, is this clear? How do we determine the direction of this right hand? What is the direction of the angular velocity? I want to see everybody. I want to see your right hands. Not just texting, but also showing the direction of the angular velocity. Yes. This is the right-hand rule. Now, since the angular velocity is a vector, angular acceleration is also a vector. So let's look at again this example. Just rotate it in one direction. What is the direction of the angular velocity? Downward. Now it is moving faster. So what is the change in the direction of the angle? The direction of the change in the angular velocity is downward, so angular acceleration is downward. Now, the angular velocity is in which direction? Angular velocity is still downward. The change in the angular velocity, so the angular acceleration is pointing upward. Now, angular velocity is upward. The change in the angular velocity is again upward, so the angular acceleration is in the upward direction. Now, I will just give a kind of a mathematical break. Remember when we were discussing our manipulations of the vectors, we talked about the addition, the subtraction, multiplication by a number, scalar multiplication. Then we didn't discuss what is vector multiplication. Now, when we talk about vector multiplication, what we mean is that you take a vector, you multiply it with some other vector, and the result will be a third vector, not just a number. Now, this C is a vector, and if you just say, let's say this is A, this is B, this is the angle between the two, just theta. Now, the length of this vector C, the magnitude of the vector C, we define it as the product of the magnitudes of A and B. This time it is the sine of the angle between the two, not the cosine. If you remember in the scalar product, we define the scalar product as the product of the magnitudes of these two vectors multiplied by the cosine of the angle between the two. Now this time it is the sine. Now the direction is determined by the right-hand rule. Now, how do we apply the right-hand rule? Let's just suppose that this is my vector A, this is my vector B. I would like to calculate A cross B. Just imagine that there is a rotation. A vector is rotating towards the B vector. What is the direction of the angular velocity? That is the direction of the angular, this cross product. So if this is A, this is B, if you would just imagine the A vector to just go straight to the B vector, rotating the A vector to the B vector, then the angular velocity of this vector is the direction of A cross B. Now, if you imagine it the other way around, this is A, this is B, if you would calculate B cross A, then you would start from B and imagine it is rotating towards A. Then the right-hand rule, just curl around the direction of rotation. This is the direction of B cross A. In the case of A cross B, this is the direction of A cross B. So they point in opposite directions. If you remember in the scalar product, whether we take the scalar product of A and B or B and A, they meant the same thing. But in this case, A cross B and B cross A, they are vectors of the same magnitude. They just point in opposite directions. Now, this cross product we will be using often, so if you think that it's not clear how we obtain the direction, we can repeat it. So is the right-hand rule clear? Those sitting at the back? Is it clear, the right-hand rule? Vector A, vector B. What is the direction of A cross B? This is A, this is B. A cross B. A cross B. Up or down. Right-hand rule, just imagine you are rotating the A vector towards the B vector. So this is the rotation. Wrap your 4 fingers in the direction of rotation. Your thumb will point in the direction of A cross B. So this is the direction of A cross B. B cross A, just imagine you are rotating the B vector towards the A vector. Then the angular velocity vector of that the direction of the angular velocity vector of that rotation is the direction of B cross A. So B cross A, this is the rotation, this is the right-hand rule. Let's choose a coordinate axis. This is the x-axis is just out of the screen. Just imagine this is out of the screen. This is the y-axis. The z-axis is, in this case, conventionally chosen to be upward, such that x cross y is always equal to the z vector. Not minus z vector, it is the z vector. So you see this is x, this is y, If you calculate x cross y, just imagine the x hat vector rotating towards the y hat vector, this rotation, the angular velocity vector of that rotation is pointing upward direction. So that is the z direction. And similarly, if you just calculate y cross z, okay, this is y, this is z. If you want to calculate y cross z, y, just imagine this y hat rotating towards the z hat. This is the rotation. So the right-hand rule, this is the z direction. Now this is the x direction. And finally, z cross x hat will be equal to y hat. And we already know that if you change the order of the vectors, the cross product changes sign. This is how I wrote the last column over there. X cross x. One or zero? Now remember, first of all, 1 cannot be the answer because this vector product gives me a vector. And the magnitude of that vector, you see the magnitude of the cross product is the product of the magnitudes of both of those vectors times sine of the angle. So if you have a vector, take the cross product with itself, the angle between the two is 0. Sine of 0 is 0. This is sine. So cross product comes with a sine. This is y cross y is also 0. Z cross z is also 0. In fact, any vector cross product with itself will always be 0. Because the angle between a vector and itself is 0, sine of 0 is 0. Now this also allows you to calculate, for example, ax hat plus a y hat cross, let's say, bz z hat. You can calculate the cross products of such vectors written in terms of their components. Because just like ordinary vectors, with ordinary multiplication, we have this distribution property. This will be ax bz x cross z plus a y bz y cross z. This is a x bz. Well, x cross z is minus y hat. A y bz, y cross z is x hat. So you can just calculate the cross product of vectors given in terms of their components. Now let's use this cross product to describe our rotations. So let's just take our rigid body. It is rotating around this axis. Let's assume that it is rotating. This is the angular velocity vector. So this means a vector pointing out of the screen and this means a vector pointing into the screen. So just imagine that these vectors are arrows. So if the arrow is pointing towards you, you will see the tip. This is this dot over there. If the arrow is pointing away from you, you would just see the cross made by the feathers at the end of the arrow. So these are the cross made by the arrows at the end of the arrow. So that's where this notation comes from. So here, this is the angular velocity vector, so like in this sense. So if this is the angular velocity vector, is this object rotating clockwise or counterclockwise? If it is the angular velocity vector is pointing towards you, that is your thumb of your right hand pointing towards you, and your fingers This is how the object is rotating. So it's rotating like this. That is the counterclockwise sense. You see, the angular velocity vector is not counterclockwise. The velocity vector has this one direction only. The object is rotating counterclockwise. This is the rotation. And the angular velocity vector is not this one. This is not the angular velocity vector. This is the angular velocity vector in that direction. Now let's look at this point. So we know that it has a linear velocity. It will have, this is the linear velocity. Let's say it is at a distance r from the rotation axis. We had already seen that the velocity of this object is equal to r times w. What is the magnitude of r cross w? This r is the position vector. This vector is the r vector. This is my r vector. So what is the magnitude of this r cross w? Magnitude. Sine of the angle between the two. What is this angle between the two? Sine of 90 degrees is just 1. So this is equal to r cross w has the same magnitude as the velocity vector of my object. So okay, we started with r cross w. We said that okay, this is something that has the same magnitude as the velocity vector. So what can you say about the direction of r cross w and the v velocity vector? What is the direction of r cross w? This is r, this is w. R cross w, just imagine this r vector rotating towards w. Your forefingers going in the direction, in the sense of the rotation, then your thumb is pointing in this sense. So r cross w is in the opposite direction of w. This is the direction of r cross w. Well, omega cross r is in the same direction as the velocity vector. You see, this is 90 degrees, it's doing circular motion, and in any circular motion, the velocity vector is always perpendicular to the radius vector, and r cross w is also always perpendicular to both r and w. So omega cross r is in the direction of v, and it has the same magnitude as v. So we have these two vectors. On one hand, I have omega cross r vector and the velocity vector. They both have the same direction, as we have seen over here, and they have the same magnitude. But that is what, those two things are what describes a vector. A vector has a direction and a magnitude. If you have two vectors that describe the same, that have the same magnitude and direction, then those two vectors have to be equal. So in vector form, we can write the velocity vector of an object, of a point on a rigid body, in this form in terms of the angular velocity vector. Now, any questions on this one? Okay, so let's continue with the kinetic energy. Now we know the kinetic energy of point objects. The kinetic energy would be just 1 over 2 mass of that point object times the velocity of that point object squared. So if you have just a bunch of point objects, this will be the total kinetic energy. Now we will take this rigid body. This is my rotation axis. Let's say omega is pointing out of the screen again. I can just, well, this is not a point object, but I can just imagine that it's a collection. It's just a collection of very small point-like objects, masses. Now, if I look at one of them, let's see, if I consider this one, right at that point, this is its position vector. And we also know that this will be its velocity vector. And we know that Vi will be nothing but omega times Ri, the speed of the object. The speed of that point is nothing but the angular velocity of the rigid body as a whole multiplied by the distance from the rotation axis. Okay, you see, this Ri, don't confuse it with the distance from the origin. Ri in this case is the distance from rotation axis and not from the origin. So if you just imagine this one, this rotation, this object, I can take the origin to be here on this test. That Ri for this point over here is this distance, not the distance from the origin. Now if we put this back into over here, we see that the kinetic energy is in fact 1 over 2 mi omega squared times Ri squared. Now omega for all the points on my rigid body is the same. Omega for, in fact, it's the angular velocity of the object as a whole. I mean, it doesn't change it's not different for this point or for that point or for this point. They are all the same omega. So I can just take it out of the summation sign. 1 over 2 mi Ri squared times omega squared. So this is the kinetic energy for rotations, or the rotational kinetic energy is equal to 1 over 2 mi Ri squared times omega squared. Now just compare it with kinetic energy is equal to 1 over 2 mv squared. Just this is the one-dimensional case, or the three-dimensional analog. So you see, they have almost the same form. We have the 1 over 2, 1 over 2. We have the linear velocity. Now here, this is the angular velocity with omega squared. Here we have the mass of the object. Here for rotation, we don't have the mass, but some quantity related with the mass of the object. And this quantity is what we call the moment of inertia. This is just a definition. Now we will see several more examples, but we said that, position, the analog in rotational motion is the angle. We have the linear velocity, we have the angular velocity in rotations. In linear motion, we have the linear acceleration. In the angular case, we have the angular acceleration. In the linear case, we have the mass. The place of the analog for rotational motion for the mass will be this quantity over here, this moment of inertia. we will see several more places where this combination will arise. So that's why, in fact, we are making such a definition. It just turns out to be useful so that everybody starts using it to describe the properties of a rigid body. Now, to calculate it, what you do is let's do an example. Let's just imagine that, okay, let's have the x and the y axis. Let's put some mass over here. Let's put another mass over here. A fourth one over here. The fifth one over here. And let's assume that they are all a distance a from the origin. We can imagine them to be connected somehow so that it will form a rigid object. Well, for example, this is a simple case where we can actually calculate the moment of inertia. You are just summing over all the masses making up your system. So we have, in this case at least, we have 4 of them. 1, 2, 3, 4. We'll start from the first one, that is m times a squared. For this one, it is also the same distance, m times a squared plus m times a squared, but all of them contribute equal. I is equal to 4m times a squared. That is, for a simple system, we can calculate the moment of inertia in a straightforward manner. Now, if this whole thing is rotating with angular velocity omega, in that case, the moment of inertia would be the kinetic energy. Kinetic energy would be 1 over 2 4ma squared omega squared. Now, to calculate the kinetic energy of a rigid body, you don't have to go and calculate the kinetic energies of each one of the masses making your system and sum them up. You can just, if you know the moment of inertia, once you determine the moment of inertia, you can just calculate 1 over 2 moment of inertia times omega squared. In a sense, it will be a shortcut to calculate the kinetic energy. Let's do a few more examples. For example, this one. If you look at this one, well, most of the mass of this object is either on the rim, here, or very close to the rotation axis. Well, if you are very close to the rotation axis, you say this is the definition of the moment of inertia. Masses very close to the rotation axis, since these Ri will be very small, in this case, for this rotation, if you consider the masses over here, they are very close to the rotation axis, and they do not contribute to the moment of inertia. So the moment of inertia of this wheel will be more or less only given by the moment of inertia at the rim, of the masses on the rim. So we can calculate the moment of inertia of a ring mass. Let's say it has a radius or a total mass m. Well, again, it's not a point mass. It's neither just the sum of 4 or 5 point masses, but we can still just divide it into very small parts. And then the moment of inertia is just the mass of one of the segments. Well, the distance of all of these segments from the origin is the same. It's a ring. So all of these Ri is equal to R squared. So this is equal to mi R squared. This is m times R squared. This is the moment of inertia of a ring for rotations around this axis. This is the moment of inertia only for this rotation. So if you take this wheel and if you want to rotate it around such a perpendicular axis, the moment of inertia will be different. You cannot use the same moment of inertia for all kinds of rotations. For this one it will be different. If you want to rotate it not around this axis but around a point on the edge, for this rotation it will be different, etc. For each one of them you have to calculate them. But of course for these cases, for example, if you know the moment of inertia for these rotations, we will see next week that there is an easy way to obtain the moment of inertia for this rotation. And again, if you know the moment of inertia for these rotations, it will be easy to calculate the moment of inertia for these rotations around some other point. Now, but those things we will learn on next week. Now, any questions? I see that you are already dead about all these rotations, all these new concepts, so I will not be talking about new rotational concepts.
Why R squared?
Well, that is what comes out. You see, when we didn't really define it, we didn't define it a priori. We were interested in calculating the kinetic energy for a rotating object. And we just saw that the kinetic energy could be written in this form if we have a rigid body. Now, of course, if this were the only place where this combination appears, then we wouldn't have defined such a concept. But this combination appears in quite different places also. So rather than writing this sum all the time for different quantities, we just give it a name. So for example, here is one of the examples where the shape becomes important. For the translational motion, we didn't care about the shape. The only thing that determined the behavior, the translational behavior of an object was its mass. If two objects have the same mass, for example, they have the same acceleration under gravity. Whether they have one shape or another doesn't make any difference. Now, in this case, we see that the shape matters. If you have two objects of the same shape, but one is smaller than the other one, like if you imagine you have a cylinder, one is empty, one is filled, the cylinder which is filled will have a larger moment of inertia. The one that is empty will have a larger moment of inertia because most of the mass is at the edges, so the R will be larger for most of the masses. So the moment of inertia will be larger for the empty cylinder. For the filled cylinder, assuming they have the same mass. If the cylinder is filled, they have the same geometry. If the cylinder is filled, in that case, some of the masses will be close to the rotation axis, so they will not contribute to the moment of inertia. So that's why it will have a smaller moment of inertia if the cylinder is filled. Now let me ask you one question. Do you have any other questions about rotations? Yes? Where? Okay. Well, you see, these are two different configurations. But the total mass of this object is 4m. In the other example, the total mass is m. Now, you see, in this example, the mass doesn't have to be distributed uniformly over the ring. The previous example, this one, is in fact nothing but a ring. This is a ring. But the mass is not uniformly distributed. It is localized only at 4 points. But whether it is localized or not, at least in this special case, as long as you have a ring, the moment of inertia for rotations around this center is always the mass of the object multiplied by the radius of the ring squared. Okay. Okay, you have already seen this. I will show it probably a couple of times more. Okay, rotate it. Fast. Okay, enough. Okay, good. Okay. So, what is the center of mass is doing? The motion of the center of mass. What is 0? No, I mean, what is the motion of the center of mass of this object? What is the motion? The center of mass. Rotate it. A bit faster. Hold it, hold it. Rotate it, no, only over there. Fast. Okay, enough. Okay, fine. Okay, rotate it fast. Once. Okay. So what is the motion of, where is the center of mass of this wheel? At the center of the wheel, right? Somewhere over there. So is it fixed? It's not fixed. Is it moving? What kind of a motion does it do? It's not rotating around itself, it's rotating around some axis, right? It's doing some circular motion. So does it have an acceleration? So what is the force causing that acceleration? If it's accelerating, what's the direction of the acceleration, by the way? Give it a try. Hold it tight. Pull it strongly once. Yes. Okay, so what is the direction of the force? Okay, what's the direction of the force? Towards the center, right? The center of it's doing this circular motion, and the force is always pointing towards the center. It's horizontal. So what is creating that horizontal force? Gravity is perpendicular. So it's not due to gravity. But we have to have some force, because we already have seen in the previous weeks that if the center of mass has an acceleration, there has to be some external force acting on my object that creates that central acceleration. So what is that? What is the force? Okay, we already know that there should be a force. It has to be horizontal. It has to be towards the center. But what is exerting that force? It's not gravity. Gravity is perpendicular. This is a horizontal force. The tension. The rotation. No, even if you do this even if the Earth was not rotating, okay, that is not a force. So we have to, what is the force?
Why not tension?
The tension. Is it the tension? No, why not? The tension is upwards, are you sure? Gravity is definitely downwards, that's we are sure. Is it straight? No, this string, is it straight? Well, maybe, I should have brought another string, which will go just straight down, so we would be able to compare. That is for next week. Now, any questions? It will be the tension. You see that this string cannot stand straight up. It has to move to one side, so that it will start exerting this center of force. Any questions before you go? But the important lesson is, if the center of mass is moving, there has to be some force acting on it. You cannot just say that, okay, the center of mass is rotating because of the angular velocity. There has to be some force. It is only external forces that can accelerate the center of mass. Okay, see you next week.